Okay, so do you want to make that official? We'll do the test the Wednesday after spring break instead of the Friday before spring break.
Yes.
Sure. Okay, that means I got tests in all 4 of my classes on that same day.
Just think you have that much more time to make the test and relax.
True.
We're
True.
just helping you. I don't know.
So
we have to.
You what?
I don't know if that's in our favor to give you more time to look up.
Yeah. Oh, I could just thought of another question. Put it on there.
All that really means is we're going to have time to figure out a proof problem.
Well, I don't do proof problems in this class. You're lucky there.
So we'll have, if we're going to review the Monday before, then we'll have the review before. When we go to spring break.
Right. Yeah, I can give you the review sheet to work on over spring break. And I don't want you doing anything over spring break except studying for this test.
Can you have the key posted as well?
Right. What?
Can you post the key as well?
When you're done with the review, I can give you the key, yeah.
Can I have it beforehand?
No.
That way I know what I'm doing?
No, that's... Research has shown the best way to retain information is to struggle with it on your own for a while and then have someone show you how to do it. Not have them show you how to do it with you watching. Because then you're like, oh, it looks so easy when somebody else is doing it, but as soon as you try on your own, it's not so easy, right? So you'll get the review. You'll get the key to the review after you've attempted the review. Then you can go see how to do the ones you didn't know how to do.
So if I email to you with the spring break, you can do all back.
Yep, you can do that. You can do that. Okay, so today, to finish up chapter 12. Somebody's going to have to help me. Let's see. View. Browsers. I'm starting to remember this. Okay, here we go. So we did two-way or one-way ANOVA. And we finished up last time. We showed how to do it in Excel. And we did how to get the sum of squares for the model, sum of squares for error, all that stuff, and the F-test and what it means, and then tests. And so I started to say, and tests for the different means. And that's not, we haven't done that yet, so that's today. So one-way ANOVA, means comparisons. So the idea here is that when you run an ANOVA, a one-way ANOVA, and you've got some factor, and let's say it has 4 levels, right? So I do drug studies. So let's say we have the one factor is treatment, and it has 4 levels. They got placebo, low dose, mid dose, and high dose. So 4 levels of treatment. Everybody following me? And the scores are allergy symptoms or something. He blew his nose, made me think of that. Right? So allergy symptom scores. So I run my one-way ANOVA, and lo and behold, the F-test says, reject the null. All right? So F-test rejects null. What can I conclude from that?
That at least one of the means is different.
At least one of the means is different than the rest. So, does that mean my drug works?
No.
Not necessarily. It might be the placebo is better than the others, right? So I need to do means comparisons to decide which of the means are different. The F-test says at least one of them is different. We do means comparisons then to try to figure out which one or which group or whatever, which of the means are different from others. So, pairwise comparisons, we'll start with that, right? So, i.e. mu1 equal mu2. We want to check and see if that's true, so I put a question mark. Is mu1 equal mu2? Right? Now that looks an awful lot like the null hypothesis from a t-test. So guess what? The means comparisons are going to be done with t-tests. And the only difference from the 2 SAMP t-tests that you did back in MA140 is instead of entering the standard deviation from group 1 and the standard deviation from group 2 into your calculator, it doesn't use the pooled estimate from those 2 groups. It uses the pooled estimate from the one-way ANOVA, which is all groups. Right? So it's going to use the root mean squared error for the standard error of the mean rather than just looking at those 2 groups. So it's not, you won't get quite the same test statistic or p-value that you would get if you just focused on those 2 groups, group 1 and 2, and entered the means and standard deviations into your calculator and did a 2 SAMP t-test. You'll get a slightly different result. Right? But these are pairwise means comparisons. So how many pairwise comparisons will I have if I have 4 treatment groups?
3.
Not 3. Not 7, not 8.
6.
You're going to narrow in 6. Woo! How'd you get that? I kept guessing till you said woo! Right? How many groups are there? 4. How many do you take at a time to do a pairwise comparison? 2. So 4, choose 2 is the number of, right? So 4 choose 2. So it's I choose 2. And that's in math, that's how you write that. Or on your calculator, I choose 2. Right? That's how many comparisons there are. I don't really care that you know how to compute that or anything, but just have an idea. Do you know how this works? Good. 4 factorial when I have 4, but it's I factorial over 2 factorial times I minus 2 factorial. So if I is a 4, you got 4 factorial over 2 factorial times 2 factorial. 2 factorial is just 2. So 4 factorial is 4 times 3 times 2. The 2 is going to cancel. You got 4 times 3 over 2, which is 6. Right? So I equal 4 gives 6. Right? So you can think of it like this. I had placebo, low, mid, and high doses. So you can take placebo versus low, mid, high. There's 3 of the comparisons. Then you can take low versus mid and high. There's 2 more. And which one am I missing? Mid versus high. And there's all 6. Right? Now, the problem with this, statistically, there's an issue here. And it's called multiple comparisons. Have you ever heard this term? Okay, multiple comparisons. Let's say that I have a research study. No, let's say it this way. There is a hypothesis out there among researchers in the United States, but the null is actually true. Right? But there's 100 researchers around the country that are all studying the same thing. Right? They all do a statistical hypothesis test of the data they collect on this. How many of them are going to reject the null? Just by random chance. 5. Why? Because that's alpha, right? The significance level. Remember what that means. It's the probability of a type 1 error. And type 1 errors, the probability of rejecting the null given that the null is true. So when we do multiple comparisons, we're doing multiple hypothesis tests using the same data. So even if the null is true for all of them, we expect to reject 5% of them just by random chance. So technically, you should do some kind of an adjustment to your alpha level. Don't test them at 0.5. Test them at some lower alpha so that overall you only will have you'll have a 5% chance of at least one type 1 error. What? Okay. I'm doing 6 comparisons, right? So if I do 6 comparisons, if I do them each at a lower than alpha, then the probability of making at least one type 1 error among those 6 can be controlled at the 0.05 level. But if I do them all at the 0.05 level, then the overall probability, actually it turns out, is 23%.
Wow.
You have a 23% chance of making at least one type 1 error for 6 independent comparisons where the null's true on all 6. 23% chance. So that's your true, what they call experiment-wise alpha level. Right? So we control the comparison-wise alpha level at some low number so that the experiment-wise stays at 0.05. Now this class being not too technical of a class, we won't get into exactly how all that is done. We will only focus on one of the methods for controlling that alpha level. There are literally 100 of them out there, right? Because they're all approximate. And when you have a theoretical statistician publishing papers in stat journals, the word approximate is like gold. It's like, oh, that means there's lots of ways to do it. So I've got to find a different way to do it than anybody else has done it, and I can publish that. Right? I actually have a publication in multiple comparisons methods.
Is that what your PhD was in?
No, it was not in that. But so the method that we're going to use to control, so control type 1 error rate. Adjust alpha for each comparison. And we will use the Bonferroni procedure for 2 reasons.
Is that 2 R's or 1?
It's 2 R's. That's a guy's name if you didn't guess. Bonferroni. Guess where he was from? Italy. Of course. Sounds Italian, doesn't it? Bonferroni.
Sounds like awesome.
It does. So the Bonferroni procedure, there's 2 reasons why we're going to focus only on that one. First of all, it's the most popular one. And the reason it's the most popular is because it's the simplest. Right? It's really easy to figure it out. The other procedures don't really have a closed form solution, but they are more accurate. They work better than Bonferroni. He's the first one that came out with it, did a real easy thing. What he does is he takes the overall alpha, what I called the experiment-wise alpha a minute ago, take the overall alpha and divide by k, where k is the number of comparisons. So how many pairwise comparisons am I doing? 6. So if I want to control, if I want my overall type 1 error rate to be 0.05, which is what we would normally use, then I just take 0.05. That's not a very good looking 5. Take 0.05 and divide by 6 and give me that as a decimal. Brent, you're holding your calculator. Go. What is it?
0.008 repeating.
0.00833 repeating. Right? So now you do each of the t-tests for those 6 pairwise comparisons, and if the p-value is less than that, you declare them statistically different. Otherwise, you say not enough evidence to reject the null. Non-statistician researchers hate this. because they want to do the 0.5 level because that's what they've done their whole life. And you show them a comparison, like I check placebo versus low dose, and I say, there's not a significant difference. And they say, what, the p-value is 0.01. That's significant. No, it's not, because it has to be less than that, right, to control the family-wise or the experiment-wise alpha level, right? So it's kind of counterintuitive, and people get so used to this magic 0.05 that they don't like it when you chop that in pieces. But that's what you have to do so that in the long run you won't make type 1 errors when you do this. Question?
This is just logical because you're multiplying the 0.05 error by the 6 amount of comparisons. So you divide by the 6 amount of comparisons and you come out with the 0.05 that you're looking for, which then becomes that. This is all very logical.
It is all very logical. Unfortunately, the math doesn't work exactly like that. So that's why it's approximate. And Bonferroni knew that. And he said, this is conservative. Ooh, there's a word. Conservative and liberal in statistics don't mean the same thing as they do in politics, but sort of they do. When we say it's conservative, we mean this number is actually smaller than it would have to be. All right? So instead of falsely rejecting 5% of the time, you're actually less than that. You're going to falsely reject even less than 5%. Right? And the reason it isn't just that is because these comparisons are not all independent. If they were all independent, then dividing by 6 would work out. But they're not all independent. Why are they not independent?
You're using the same data.
You're using the same data and the same group. So the same placebo is being used 3 times. So if you got an abnormal placebo sample, then it affects 3 of those comparisons. They're not independent. Right? So there are other procedures that take into account the level of dependence and don't make such a big chop on that. Yeah.
And I'm assuming that's just a 2-sided p-value to be less than that, right?
Right.
Okay.
2-sided p-value. It all works if you're doing one-tailed tests also, but we rarely do one-tailed tests. We do ANOVA. Yeah.
So if you correct for that they're not all independent, it would actually be chopped by less than 6.
Right. It would be chopped by a number less than 6.
Okay.
Yeah. And then, like I say, there are literally probably 100 out there in the literature, different ways to do the same thing. And they're not, you can't say this one is best. It's this one's best if you have data like this. But if you have data like some other data, then this one is best. And that's why there's so much room for all these different procedures out there. Because there is no universal best. Okay? So now let's see how to do these comparisons. All right? So let's introduce a concept called a contrast, which is a more general type of comparison than those pairwise comparisons. And we'll show in a second that each of those 6 pairwise comparisons forms what's called a contrast, but there's literally an infinite number of possible contrasts you could do. Right? So contrast between means. Is any hypothesis of this form that's supposed to be the Greek letter psi, right? Is that psi? Yeah, I think that's psi. I kind of get confused. Looks like a pitchfork, right? So equals 0 where psi is equal to a linear combination of the means a sub I times x bar sub I. So a linear combination of the group means. But to be called a contrast, which then allows us to say the null is that thing is equal to 0, the sum of the AIs, the sum of the contrast coefficients, must be 1. I'm sorry, must be 0. Okay? And I have a notational error here I want to fix. This shouldn't be X bar. I'm doing Greek letters. So it should be a mu. And then we're going to estimate it. So this should be mu sub I. And then we estimate the point estimate is we use a lowercase c, so it's psi and c. And sometimes they use the Greek letter to try to sound kind of like the regular letter. So c for contrast is equal to the same linear combination, a sub I, but now times x bar sub I. That's your point estimate of that. Okay? And again, I'm not putting the indices on the summation, but that's assumed. But this is across all groups. So I equal 1 to capital I. Okay?
So why are the A's summing to 0?
Why are the A's summing to 0? Well, that is because you can estimate any linear combination of the means that you want. But then what would you test to see if they're equal or not? So what I want to do is I want to compare a linear combination of the means and see if that linear combination is equal to 0 or not. Then as long as the sum of those A's is 0, that will happen. So for instance, test mu1 equal mu2 as a contrast. That's equivalent to null hypothesis psi. I have a subscript on my psi that shouldn't be there. This makes it sound like it's specific to a group. It's not. So just erase that subscript. I get all subscript happy when I do these things. Right? So just Greek letter psi. But psi, I got to get rid of this sub I here also. Okay, so psi equals 0. Give me a linear combination with the right AIs that give me this. Well, the first thing is I want to test it equals 0, so I need to move the mu2 to the other side. So mu1 minus mu2 equals 0. So what's my psi? What are my A coefficients? It looks like an alpha, but it's an A. What are the coefficients? This is 1 times mu1, right? So A1 is a 1. Plus, because I'm summing, something times mu2. What is mu2? Or what is A2? Coefficient, it's a negative 1. Right? So if A1 is 1, A2 is negative 1, then the sum of the coefficients is 0, and I have a comparison between two means. So a pairwise comparison is a contrast. It's called a contrast. Right? What would I do? See if you can do this one. Mu1 minus mu4. I didn't finish out what the other A's are, but what would A1, 2, 3, and 4 be? That's a 1, a 0, 0, negative 1.
Could there be anything that sums to 0?
They can be anything that sums to 0. That's right. But this contrast with these coefficients we'll test that. Now, the reason that we want to allow other possibilities besides just pairwise comparisons is because sometimes it's of interest to test one group versus the average of the other groups. For instance, this setting, I've got one group that got placebo, 3 groups that got an active drug. So maybe if I assume, well, it doesn't really matter what dose you get, then those other 3 groups are really the same thing. So let's average those 3 groups together and compare them to the placebo group. Right? So here's what I want to test. Null hypothesis is that mu, and instead of, no, I'll go ahead and use the 1. So 1 equal 1/3 times mu 2 plus mu 3 plus mu 4. So placebo mean is equal to the average of the 3 group means. What are my contrast coefficients? Well, all you got to do is solve this thing, get everything to one side and get a 0, right? Set it equal to 0. So let's do the algebra. Mu 1 minus 1/3 quantity mu 2 plus mu 3 plus mu 4 equal 0. Right? Now distribute the negative 1/3, and I got mu 1 minus 1/3 mu 2 minus 1/3 mu 3, so on. Now you have a linear combination. So what are my AIs? Let me erase the ones that are up here. What are my AIs? 1, negative 1/3, negative 1/3, negative 1/3. Do they add to 1? I mean, add to 0? Yeah, they add to 0. So that is a contrast. Isn't that slick? Sometimes, you know, I've done clinical trials where this very contrast was an important test for the researchers to do. They say, well, I've got these different dose groups, but I don't really expect there to be much difference between them. My dose response profile I expect to be something like this. Here is the value on placebo, and then my other 3 doses I expect to be, you know, fairly close to each other. Let's just average those 3 together, compare them to this one. There's your contrast.
So you don't use the more precise one? Or in the drug trials you like to use this conservative?
Oh, I'm not talking about the Bonferroni thing. This is independent of what method you use to adjust your alpha. We haven't said anything about alpha here, right? That only comes into play. The alpha only comes into play when we've done the whole test, gotten our p-value. Now, what do I compare that p-value to? That's when the Bonferroni thing comes into play. Okay? Now, if this dose response was different, and I expect that the low dose isn't really going to work, but the other 2 doses will work, what contrast might be of interest here?
The placebo, the low dose, and then the other 2 combined.
Okay? So combine these 2, combine those 2, then see if they're different, right? Give me my contrast coefficients. See if you can figure out what they would be. To compare the average of these 2 to the average of those 2.
1/2, 1/2, negative 1/2, negative 1/2.
I hear one person talking and a whole lot of people staring at me like
I agree with that.
deer in the headlight.
You said that was mu 1 plus mu 2 over 2.
Exactly. So let me just go to another page. So what Corey was figuring out, well, if you want to compare the average of the first 2 to the average of the second 2, that's 1/2 mu 1 plus mu 2 equal 1/2 mu 3 plus mu 4, right? That's what you want to compare. The average of the first 2 to the average of the second 2. Now, rearrange algebraically, make a contrast out of it. and you get what Taylor said. So you get 1/2 mu1 plus 1/2 mu2 minus 1/2 mu3 minus 1/2 mu4 equal 0. Now my contrast coefficients are 1/2, 1/2, negative 1/2, negative 1/2. They sum to 0, so it's a contrast. And you get the comparison you want. Phew! This is fun. Now, here's how you set up your hypotheses with your contrast. The estimate of this, right? So, observed value is the same thing but with x bars in it. So, sum of a, I, x bar I, right? So we know what the AIs are. We replace all the mu's with x bars, and we get this thing we call C. So we need to form a test statistic. Now, we'll test your statistical inferential insight. How are test statistics set up? Almost all test statistics are formed in a similar way. You take the point estimate minus... No, that's a confidence interval. Not yet. We want test statistic. But how are test statistics set up? Observed and expected.
The point estimate divided by the standard error.
Okay. One little thing extra. I already told you these will be t-tests. So t equals the point estimate of the contrast, which we've called C. So C minus, and then what do we subtract off?
R.
This is observed, right? C is observed, so not observed, but what? Expected. Expected if the null is true. If the null is true, what would we expect that value to be? Hint, there's the null. 0. Right? So we expect it to be 0, so I don't really have to subtract it off, but just to illustrate. So it's just like the t-test statistic for a regression coefficient. You take the point estimate of that coefficient minus the null hypothesized value of the coefficient, which is 0 usually, divide by what? Standard error of that observed value, or the point estimate, right? So we need the standard error of C. We'll get a computed value of C, we'll divide by its standard error, and then we have a t-test statistic, right? Okay, so standard error of C, that's all we need, and we've got our test formed. So the standard error of C, how do you suppose you get that? You'd probably use your calculator. Remember what the standard error was when we had, so this is scratch paper, which I'll go back and erase. But if we were just doing a 2-sample t-test, what's the standard error? We did it the other day. It was S sub p times the square root of 1 over n1 plus 1 over n2. Right? It's very similar to that. It's SP times the square root, only now I need to take into account the contrast coefficients. here, what were the contrast coefficients for a 2-sample t-test? We did that one first. 1 and -1. So this is contrast coefficient squared over N1 plus next contrast coefficient squared, so to get rid of the negatives. Right? So that's exactly what it is. It's just the sum of AI squared divided by Ni. So it looks very similar to this as long as you recognize that, oh, that is just a contrast. Right? The comparison between two sample means is a contrast. But this makes it more general. Now, the only thing to remember is, what the heck is SP? That P stood for something. Pooled. Right? So SP is the pooled estimate of standard deviation. And from an ANOVA table, where do you get that? What did you say? Yeah, but where do you get it off the ANOVA table? Laura? Root mean squared error. Okay? So that's what I said earlier, that if I just compared mu1 to mu2 and did it the old-fashioned 2-sample t-test, I'd be throwing away half my data. Because I'm not even looking at groups 2 or 3 and 4. I'm only looking at groups 1 and 2. And I'm getting this SP from just those two groups by this formula. Well, now I'm using all 4 groups to give me the pooled estimate of standard deviation. All right. So then our test statistic, we go back to this page. Standard error, I can write that as C, and I don't have to write the -0. And then SP square root of sum AI over NI.
I thought you had AI squared.
I do. I was just seeing if you were watching. AI squared.
And then SP could just be also the square root.
Yeah, and if you want to, in your notes, you may want to substitute that in and say that's square root of mean squared error. Okay?
So those are for all the groups, or for the groups that you're looking at, for the AI and NI?
It's across all groups. But what happens, like, well, I've erased it. But what if I want to compare I erased it. I remember what we had here for this comparison? I had 1, 0, 0, -1. Right? So this would be 1 squared plus 0 squared, or I'm sorry, 1 squared over N1 plus 0 squared over N2. So what happens with the ones that have a 0? They go away, right? But the ones where I had this, all 4 are going to be involved because all 4 groups get used in that contrast. Okay? So when you come to here, that sum across all the groups, sometimes the AIs will be 0 for some of the groups. So they don't come into play.
So do you have to do a test like this, like a 2-sample test to see if you can combine 2 groups? Or is it just kind of like by eyeball? Does that make sense? Like how much is too much to be the difference between placebo and low dose?
You ask a really interesting but somewhat controversial question. Did everybody understand what he's asking? This picture.
Like how different is different?
Yeah. Can I just look at this and go, oh, I'm going to combine that and that, right? Those are what we call post hoc contrasts. You looked at the data and decided, oh, I think I'll test this versus that. Contrasts should be pre-specified. Anytime that you have regulatory oversight, like in drug development, we've got to submit to the FDA. We write and sign and date and notarize practically what's called a statistical analysis plan. And it has to be finalized and signed prior to you ever looking at the data. And they know when you look at the data by the dates that the data set is time-stamped at, and all that. So the database was closed on this date. So prior to that, you have to specify this. So how do I know? I make guesses, not I, but the team makes guesses based on what they've seen in the past, earlier phase studies or whatever. But sometimes you guess wrong. Sometimes you guess, oh, I'm going to do average of these two versus average of these two. But then it turns out when you get your data back that this one is up a lot higher than you thought it would be. And now you've hurt yourself because now the average between the two is in there versus in there instead of as far, right?
You still have to test it.
You still have to test it.
You can't argue it.
Nope. I mean, you can do the post hoc stuff and say, well, it turns out that we were wrong in our guess. So here's the results when you do it the other way. But they'll say, yeah, that's nice. But here's your primary comparison, and that one was not significant. So sorry, do another study. Right?
So, but like if you don't have regulatory oversight and you're able to just figure out the best way, like would you just basically use the two? Like if you wanted to compare them to see if they were different, you would just use what we're talking about, and then you could combine them if you show that they're not that
right.
statistically
yeah.
different.
So what you're getting into is really common. Unfortunately, it's fairly rampant in scientific literature that people look at the data first, then decide what comparison has the best chance of being significant, then they go do that one, which is fine as long as you tell your audience that you did that. But if you make it sound like, oh, we went in and we were going to test these contrasts, and look, they're significant, then what you really did is what we call a fishing expedition, right? You go and just throw, a whole bunch of contrasts and tests or whatever, test this group versus that group until you found one that was significant, and then you publish that, right? Well, 5% of all those tests are going to be significant just by random chance. So if they know you did 100 tests, and now you're bragging because 2 of them were significant, then that's very different than just going, hey, look, two of these are significant. You have to know, So it really should be pre-specified. So it's the difference between what I call a hypothesis-generating test or a hypothesis-testing test, right? If you're doing ad hoc analyses after looking at the data, then you're trying to generate hypotheses for your next study. You've got to then do that next study to prove that, yeah, it really is. It's not a type 1 error, that it really was a difference.
So like in stuff that you do, you have to actually redo the study completely, right? Like you have to get new data, not...
Right. A new sample. It's not just a reanalysis of the same data. You've got to go independent trial.
So it's costly to...
Very costly. Very costly. So that's why it's really important to get studies designed right in the first place and have pilot data that helps you know what you're going to see. If you're going into your what we call registration trials, the ones you're going to submit to the FDA, without knowing what it's going to look like, then that's a high risk of failure, right? So you do pilot studies to get a sense of where these dots are going to fall and know what the right contrast is going to be. Then you invest your money to do a big study and prove it. Yeah.
So the first one where you look at it ad hoc and you don't see the data yet, you're testing a hypothesis. You're saying, I believe we're going to see a correlation based on this because we expect to see that connection.
Mm-hmm.
If you do it post hoc, what you're actually falling into is you could be reporting on, say, some hidden variable that you don't know what's
exactly.
affecting it. Gotcha.
Which caused a type 1 error.
Yeah.
Yep, that's very true. Okay, so one last thing to talk about that finishes up Chapter 12, and I'm going to run out of time before I get to SAS to show you how to get these contrasts automatically. But I'll have homework for you to do that in, but I'll have in the homework how to do it. Push this button, then go here, right? Because SAS will do it automatically. Excel will not. If you want to do contrast in Excel, you got to program them yourself. You got to ask it for the one-way ANOVA, get that output, and then it'll give you the group means and group standard deviations, and you can form the contrast on your own from that. But within SAS, it's just tell it what contrast you want. Yep.
I found this weird thing in Excel, and it might be just because like I have the big fancy version, I guess, from my dad, and it has like a stat out, like I guess out button, and takes you to like a Microsoft place where it has like a whole bunch of programs that SAS has, but it'll program it into what it
Wow, I don't even know about that.
Yeah.
So, yeah, I don't know if that came through on the video, but she's saying she has a Microsoft Excel sort of a, is it like an add-in or whatever
When
that?
I put SAS on my computer, that was when it first showed up, and it said, do you want to transfer data? And I can click any of my SAS files, and it'll compute it to my Excel.
Oh, wow, that is really nice. Yeah. So that Microsoft must have realized they were losing a lot of business to SAS, so they're trying to make it interface and do the things that SAS will do. So on our Washburn version, we won't have that access, but third parties, you might. So the last thing we need to do is a confidence interval, CI for confidence interval. So let me put 95% confidence interval for a contrast. All right. So if I'm just doing a simple pairwise comparison, I compute x bar 1 minus x bar 2. I need a confidence interval for that. You've done it for 2 sample problems. It's the same thing. We now know how to get the standard error for our contrast. So it's just C plus or minus, tell me what it will be. What? A t-critical value. Okay, I heard somebody say point estimate, and that's what C is. Right? So that's point estimate plus or minus CV for critical value. But we said these are going to be T. Anything that deals with means is going to be T. So T critical value and then times standard error of C, which we just had the formula on the previous page. So that's all you got to do. Right? So the thing to get the T critical value, the only thing you need to know is what?
Divided by
You need the degrees of freedom. Right? So degrees of freedom are same as they always have been when we did regression or ANOVA.
degrees of freedom error.
The degrees of freedom for error. And remember that the standard error had S sub P, which comes from the mean squared error. So it's the degrees of freedom in that line of the ANOVA table. So degrees of freedom are error, degrees of freedom from ANOVA.
So maybe I'm confused. Where does the Bonferroni fit in? Is that your...
Where does that come into play? Good question. So when we do the test statistic, and we get a number here, right? And let's say that number was 2.31. How do I get a p-value for that? Well, I know that has a t-distribution with error degrees of freedom, so I can use my t-CDF function to get a p-value for that. But remember to make it two-tailed. Now, to know if it's significant, that's when Bonferroni comes in. So however many of these contrasts you did, you take your alpha equal 0.05 and divide by the number of contrasts. Let's say we did 6 of them, so our p-value is 0.0, or our alpha is 0.00833. Then if that p-value is not less than that number, you say, well, I can't declare this statistically significant. I failed to reject the null hypothesis.
So K has to either equal the different groups, or it has to equal the number of groups that you've made, right?
K is number of comparisons. Right? So if I do all pairwise comparisons, plus I do this one that's the average of the first two, then I've done 7 comparisons. I would take alpha and divide by 7. If I don't care about the pairwise comparisons, and I only compare that about this one contrast, I only care about this one contrast, then I'm only making one comparison. I don't have to divide by anything.
So it's okay. It's
It's
the number
just-
that you choose, it's not the
Yeah.
number possible.
Right. It's the number that you actually do, and I always tell clients, it's however many you want to brag about. The software will give you all pairwise comparisons, but if you don't want to brag about placebo versus low dose, then you don't have to take a penalty for that one, because you're not going to say anything about it in your report. If you're only going to look at high dose versus placebo and mid dose versus placebo and nothing else, then you've got to divide by 2. Right? So it's just how many comparisons you want to brag about. All right. We're out of time, more than out of time. So I will send you by email your homework assignment and give the instructions for how to do contrast in SAS. Good luck.